So welcome everyone. Before everything, Happy New Year. I wish you a prosperous and most of all happy New Year 2025. My name is Lena Boscobian. I am Food Products and Application Manager for Chopin Technology brand of KPM Analytics. And I would like to welcome you warmly to this new episode of our webinar series dedicated to millers and bakers. This episode in particular is dedicated to how to produce a flour at laboratory level that would comply, that would be similar as the one obtained in actual milling production, thanks to efficient lab milling tools. And in particular, I'm going to focus my speech on two mills, the CD1 and the LabMill. So of course, I will be developing that a little bit further on. During the presentation, if you have any questions, please use the question and answer option. And I will try and answer all questions by the end of the meeting. So thank you very much for your attention. I hope it will not be too long, and let us start. So for the people who already joined us for our previous seminars, it will not come as a surprise. Our entire idea of quality is to start with the end quality in mind. We are making bread, we are making biscuits, we are making donuts or whatever final products for final consumers. We want this little boy here to be happy with the product we buy, and we want him to ask mommy and daddy to buy the same product again. And here the keyword is really same. He wants the same aspect, same color, same consistency, same volume, same flavor, same everything. So that means there is a real challenge for the entire industry before that to produce the same quality at every moment. So that means this is possible to produce the same final product if the baking process is under control. If the dough is always the same, or if we have the way to make it the same. And this is possible only if the flour quality is adapted to the process. And the flour quality is adapted to the process only if the milling process is under control. And this is possible only if we have an adapted wheat quality. So this is a little bit of reverse engineering in the end, starting with the end product in mind to come back to the very source of the product, which is wheat, and which will be the topic of today. If you are looking for a little bit more information about this entire strategy, please feel free to look at our previous webinars. So again, our idea is to stop guessing and start knowing. So to put data on expertise, to put data on feelings, starting with the end product. We can define and objectively measure what is a good final product, what is the good color, what is the good volume, what is the good whatever seed repartition on a bun. And this can be done efficiently thanks to vision inspection systems such as the one produced by iPro System, also a brand of KPM. You can watch the webinar on YouTube. You have the link here on the screen. And we can objectively assess the behavior of the dough to produce a good final product. And thanks to that, we can also design efficient specification to select flour based on one single instrument, which is the MixerLab. And again, the recording of this seminar is also available online. When we know what is a good flour for a specific baking process, then the miller has all the tools to produce a compliant flour with the COA. He doesn't have to waste time into looking into million aspects when he knows what to look for. And he can correct efficiently a flour that does not comply thanks to tools such as the Alvel graph and the S-Dematic, and thanks to various strategies such as adding enzymes or blending wheats or many other aspects. And this is all described in the webinar, for which you have the link in the screen as well. And this is where we are. In order to produce a compliant flour, we need to select a high quality wheat. That will allow us to produce a compliant flour with also an optimal behavior during milling process. And this can be done thanks to laboratory mills if they are representative of the industry. And this is what we are going to develop today. So before everything, we need to ask ourselves about the objective, about the end goal. Why do we do laboratory milling? Of course, the answer is simple. We need to transform grain into flour. But we don't necessarily do that for the same reason. Some people do that because they want to understand the wheat quality, the flour quality, and they want to improve it. So with this flour obtained, they are going to do baking trials. They are going to dose enzymes, for instance. And some other people, they do not necessarily want to do that. They want to compare. For instance, a miller buying a certain wheat at a certain price wants to check that he actually has the wheat he asked for. And here the reason, the objective is to compare results between specification and the actual wheat. The example of that would be to perform standardized alveograph type testings. So those are two really valid but completely different objectives. But whatever the objective, we can only have or make good decisions only if we are using a representative flour. That means if at the lab level, we have the capacity to make a flour that would represent the one obtained in the reality with a real milling process. And the second rule is to obtain a good yield. Usually flour yield is one of the major aspects of wheat performance for the millers, which is basically how we can eat. So that's really, really important. And to obtain a good yield, we need to respect good milling practices. So this is going to be the first part of my presentation to describe what are good milling practices. So this is quite simple. We have basic actions to transform wheat into flour. The first action is to clean the wheat, to remove stones and sand, and to remove any foreign materials. We need to prepare the wheat, in particular to increase its humidity, to temper the wheat in order to facilitate the extraction. And finally, we need to grind the wheat, thanks to various actions, breaking, reduction, and then we need to classify all the fractions that we obtain according to their granulometry or to their densities, depending on the processes. So if we go back to the first action, cleaning wheat, so what does that mean? That means, first of all, removing any parts that could, any mineral parts, like stones and sands. And the reason of that is very important, is very easy to understand. If we do not do that, they will go through the process and they will damage the rolls, damage the cylinders. If the cylinders are damaged, they will not perform as usual, which will have an impact on the quality of the end product. And of course, if you have roll damage, this will also mean higher maintenance costs, which is not something that we want. So removing any foreign material is important, but foreign material, is not only mineral materials. It's also non-wheat grains, such as barley or rye or whatever grain really. If you are producing a soft wheat flour, durum wheat has nothing to do in your process. So we need to remove all of those grains. And of course, why? Because if we keep them, this will impact the quality of the flour. That means higher correction costs because more enzymes, because more blending actions. And of course, it can also impact the health in case we have not removed dangerous grains, such as the one infected here in this example by ergot. Of course, this also applies at lab level. So you want to make sure that your wheat is clean from any stones, sands, non-wheat grains before processing it with any kind of meal. And then we need to prepare the wheat. We need to prepare the wheat because we want to facilitate the extraction of the center part of the grain. We want to facilitate the extraction of the endosperm and the separation from the bran, from the outer layers. The issue is the grain that we receive is usually dry. It's 11, 12%, sometimes less. And in these conditions, that's not ideal to remove the bran from the endosperm. So to ease up this action, the miller tends to soften the wheat grain by adding water and giving it time to penetrate the grain. So those are two actions, adding water and giving it time. This operation is known as tempering the grain. And this is actually very important because if we don't temper the grain correctly, like if we don't put enough water or too much water, if we don't let it enough time to penetrate the grain, then this will result in less yield, in a poorer milling yields, but also a poorer quality of the flour. Your grain will basically be harder. So that means more damaged starch, more fibers into the flour, and so potentially a flour that is less easy or different, at least, than the ones that we want to do. And of course, the same applies at the lab level. If you want to have a representative flour at the lab level, you need also to temper your grain. And then there is the objective of the miller. Whatever millers in the world, the objective is the same. The first goal is to extract as much flour as possible from a certain amount of wheat. Because this is the flour that has the higher costs, and the bran can also be sold, of course, but this is more for feed applications, and so this is less costly. So we really want to extract as much white flour, as much endosperm as possible. Increasing the yield, increasing the extraction rate, has good aspects and negative aspects. The positive is that, in general, the nutritional value of the flour will increase when we increase the extraction rate, because that means that we will extract more proteins from the outer layers, more fibers from the outer layers, and so that means, yeah, more nutrition. Also, because there is more fibers, that will increase the water holding capacity, which is always a good thing for bakers, because bakers like to bake, well, that would allow them to bake more bread at the price of the water, which is amazing. But it also has negative impacts. Of course it does. The main issue is that if you add too much bran into the mix, too much outer layer, then that will alter the gluten protein matrix. Basically, it would get into the gluten network and weakening it. And so that means usually lower volume, higher hash content and darker flour, higher microbial load as well, because if we extract more from the pericarp or the bran, then, well, we have more particles that are in direct contact with the environment. Then something that can be both good or bad is that usually we have more enzymes in the outer layer, so we will increase the enzyme activity, more protease, more lipase, more amylase activity. That can be good or that can be bad. That depends on the flour we are looking for. In any case, the shelf life of the flour will be significantly lower with a higher extraction. This is a phenomena that is very well known for integral flour, for whole wheat flour. This is the phenomena of oxidative rancidity. So in the end, this is a balance between getting the highest extraction whilst conserving the best possible quality of the flour. And this is really an art. This is where the miller shine. This is in this balance, really. And so we can wonder, what does it mean to grind the wheat? because it is actually not the same to grind wheat or to grind rice because of the very specific shape of the wheat. The wheat grain presents itself with a crease here that is not here for rice, for instance. And that means that some part of the bran is not outside, it's actually inside of the grain. It's here. And to efficiently remove the entire bran, the first action that we need to do is to separate, is to open the grain. This first action is known as breaking. And this is always done in every mills in the world with corrugated rolls. So here, when we send the wheat in between corrugated rolls, we will obtain different fraction. We will obtain bran, of course. The rest of it will go through a sifter that will separate the medium white particles, the white and fine particles, basically the flour, from the coarse red particles with bran that will go back to breaking again in order to separate the bran from the flour. Here again, the objective is really to open the grain to separate the bran and flour. And then those medium white particles that are too big to be considered flour, the idea is to reduce their size. And to reduce their size, they will be sent between smooth rolls. This is the step known as conversion. The objective is really, again, to reduce the size. And when we do that, we will again send the product through a sifter that will separate shorts, what we don't want to keep, basically the outer parts, the biggest part, from medium white particles that will go back again into conversion and from the flour. So this allows the fact to use both corrugated and smooth rolls and the fact to use sifting instrument to separate according to granulometry or density, the different fraction, they are the same all over the world. They are the same in every mills in the world. So that's really the basic of grinding wheat. And of course, if we want to be representative as the industry, we need to apply the same at lab level. So this is why this is so important for us. If we want to be representative, then we need to do the same. Most industrial mills in the world, they are equipped with they do at least 15 passages, 5 breaking, 10 conversions. And all industrial wheat in the world, they are equipped with corrugated and smooth rolls, because this is the only way to achieve at the same time good extraction and good quality of the flour. Of course, at lab level, we cannot do the same. We cannot do 5 breaks, 10 conversion, because it would be too much. But we can at least keep the same, it would be too long. We can at least keep the same setting. And this is where we can start comparing a little bit the mills that are available in the market. And here, this is just a quick comparison between what the industry does, what we do in Chopin, and what is done at Brabender or Anton-Par with the Quadrat Junior and Senior. Those are all mills recognized at laboratory level to produce flour, but we can wonder about their settings. What we want to do, well, what the industry does is a long milling diagram. Again, we cannot do the same at lab level. We cannot do the same just because if we would do the same, then that would be as long as doing the same as the industry. So that's not really the point of a laboratory tool. So of course, we have to have a shorter milling diagram. But when we look at the number of passages, CD1 and the LabMill have much greater number of passages than the Quadrat Junior or Senior. The extraction rates could be reasonable, let's say, between 60 and 70, or high. If the idea is to replicate, is to have a greater idea of the high extraction rate of the industry, then clearly the LabMill and the Quadrat Senior are the best options. Whilst the CD1 and Quadrat Junior, well, could allow to have a more reasonable, lower extraction rate. But this is where we really have a difference. The industry always uses corrugated and smooth rolls. So does the CD1 and the LabMill. On the contrary, the Quadramat Junior and the Quadramat Senior are only equipped with corrugated rolls. So that necessarily impacts the quality of the flour, and that makes the representativity of the flour less important than with the CD1 or with the LabMill. And finally, there is another point to be considered. If the method is standardized. If the method is standardized, then that gives an actual referential, an actual frame of reference to be able to compare based on a sound basis. And the CD1 here is the only instrument that is standardized in a rheological method. I will come back to that. So it all starts with knowing what you need. If you need to compare with others, then using a standard method is really the key. It really provides you with a sound basis to do trading, for instance. And for that, the CD1 really is the best option. Now, if you do not really need to compare, but still need to obtain a representative flour, but a low amount of flour to do short analysis, such as Alveo, Mixo, Rio, Farino, etc., then the CD1 or the LabMill could work. But if your goal is really easier to produce a high amount of flour to do long tests, such as baking tests, Rio F4 tests, etc., or if you really need something representative of your industrial milling process, then the LabMill is the solution for you. So again, it all depends on the objective. The idea for us is to provide an offer that would correspond to the need of the industry. And there is no one better than you to know what you need. If you need to compare, clearly the CD1 is the best option. If you need to understand what's going on, then the LabMill is really the best instrument to do that. So the questions become, what makes the CD1 a better choice for comparing, and what makes the LabMill a better choice for understanding? I started partially to answer this question, but this is what I'm going to develop now. Starting with the CD1 mill, which is a mill that has specifically been designed in order to compare. So this is a mill that is not new. We have more than 70 years of experience on this mill. This is a very simple machine made of two parts, a breaking part and a reduction part. The breaking part is equipped with 3 corrugated rolls. So we put the wheat here in the upper, equipped with an adjustment screw. And it goes here between the rolls. And here is sorted. The particles are sorted according to their granulometry, thanks to a rotary sieve. We are going to get in the end flour here, semolina, and here in the out, the coarse bread. We are going to take the semolina and place it into the reduction hopper. The semolina will fall down between 2 smooth rolls, just as in the industry, and will be sorted by granulometry again, thanks to a rotary sieve. We will get in the end flour and fine bran, and we can have 1 or 2 reduction steps depending on the amount of semolina that we get from the breaking. So that's really straightforward, and the diagram reflects that. This is a straightforward, simple, efficient diagram. We have 2 breaking steps that are consecutive. This is 1 single pass because we have 3 rolls. So for the users, it's actually 1 step. To obtain, again, flour, semolina, and coarse bran. We will take the semolina and place it into the reduction. And here we do 1 or 2 steps of reduction, depending if the semolina yield is greater than 48.5% or lower than 48.5%, in order to reduce the semolina in flour here and fine bran. So very simple, very efficient, very short. But what is interesting is that the settings of this mill, they are completely fixed. You cannot change anything in the mill. You cannot change the distance between the cylinders. You cannot change the sieves. You cannot change really nothing. The idea is really to ensure reproducibility. to get the same results from one CD1 and from another CD1, to obtain the same milling behavior, but also to obtain a consistent and identical biochemical quality flour thanks to all the CD1 mills. The rolls are very robust. We have maintenance that is robust and a long life expectancy, so no need to change them every 4 years or so. There is a centrifugal sieving, rotary sieves, as I mentioned before, that you can see here and a little bit here, which makes for a compact and reliable system. This is actually very effective if the mill is correctly calibrated and maintained. And very important, this is the only mill in the world that is standardized and associated with a rheological method. This is standardized at ISO level with the ISO 27971, which is actually the standard for the alveograph method. So in the alveograph standard, you will find a method describing how to use the LabMill, how to make sure your LabMill is giving good results, and so on, to produce a flour that is always the same according to every CD1 in the world. Being part of this ISO standard, that means that we also have fidelity data associated to this standard. We have precision for the behavior of the wheat, the total extraction, the semolinas, the fine bran, coarse bran. Here you can see the associated precision. And we also have a precision on the quality of the flour as analyzed with the alveograph. Of course, this is not just for the alveograph. You could do a CD1 test for every testing in the world for, of course, for alveograph, or also for Mixolab, for farinograph, or whatever you want. The idea here is to have fixed settings and something that you can use to compare. So really the best use of the CD1 because of those fixed settings is to ensure cross-lab comparison, to have a sound method, a single standard and universal comparison to eliminate any source of variability, to produce a flour of consistent biochemical quality, to be able to compare, again, to facilitate trading option, to make sure that you have purchased the wheat you asked for, and of course to meet specifications. So that's very suitable for testing the conformity of wheat. Just as I said, it complies with AFNOR, SEN, ISO standards, but also a ACC standardized method. What it means is that you can use that for any kind of rheological testing, but if you want to say that you comply to the alveograph standard, then you need to produce the flour thanks to CD1 mill. So really the CD1 is made to compare. And then you have the LabMill. The LabMill has been designed completely differently. It has been designed to understand and to improve. So what does that mean? That means that when we ask our users what do they like about the LabMill, about half of them, first thing that they love is the flour quality. They like the flour quality produced with this mill because this is comparable to the production. Of course, other people will tell you that it's easier to clean than other mills, which allows to see fractions, which is easy to use or has a high grain capacity. But really the main point is that the flour quality that you will get from the LabMill is comparable from the one obtained with the industrial production. So the LabMill really is the best tool to understand, and plus it is adjustable. You can adjust the cylinder gap, you can adjust the entire settings in order to obtain the most representative flour of your mill, and in order to take sound decision. So to present the LabMill a little bit further, we have again two sides. We have the breaking side with here corrugated rolls, and with, again, rotary sieving systems and different products that we will get here. I will come back to the milling diagram a little bit later on in the next slide. And here you have a reduction side, and we also do sizing actually with this mill, sizing here and reduction here. And we will get, again, different products at different steps. The idea with this mill is to respect all the fundamental rules for grinding, to have both break side with corrugated rolls, reduction side with smooth rolls, and to have a progressive sieving to really increase the extraction rate and to keep the ash content within acceptable limits, so without compromise on the flour quality. For information, this is a mill that has been designed in collaboration with what is called the Milling Value Consortium, which is a French milling association. So it really was designed by millers for millers. So here is the milling diagram. It's a little bit longer, of course, but that gives us a much more representativity, a diagram that is much more representative of what the industry does compared to the city one. And again, allows us to have a flour that is more representative. So to detail a little bit more this diagram, first, what do? You do a first breaking. So you take the wheat and you make it go through corrugated rolls. From this action, here at B1, you will get flour, first breaking flour. You will get fine middlings, you will get coarse middlings, and you will get the out. This out is still filled with flour. It's not only brown, so you place it back into a second breaking step. From this second breaking step, you will obtain again flour, fine middling, coarse middling, and the coarse brown. And this you can throw away. You take from both steps your coarse middling, and those coarse middling, you will reduce them through smooth rolls, thanks to a first sizing operation to obtain flour and fine middlings, and also fine brown. These you can throw away. That means that at this step, you have 3 samples, 3 different fine middlings. Those fine middlings, you take them all together and you place them here at the reduction level. And you make a first reduction to obtain flour and fine middlings. And you start again. Those fine middlings, you place them again, second reduction, flour, fine middlings. And you do that a third time, flour, and then what you get out from the rest, you can throw away. So that means that in the end, so just, sorry, for information, this milling diagram is patented at a French and US level. But just to tell you that in the end, you will obtain something like 14 different products and 6 different flours. So that really means you have the ideal tool to understand how your wheat is behaving through the process. What is the quality of the flour at every step? And that will allow you to strongly anticipate the actual industrial milling behavior. So the main technical differences compared with competitive mills, if we compare them to the Buehler MLU, which is considered to be the Rolls-Royce of the mills, and to the Provender Quadromat Senior, which would be the direct competition. If we take the number of break passages, we have 2 with the LabMill, 3 with the MLU, and 1 with the Quadromat Senior. We have sifting between every passages, which is the case with the Buehler MLU, not the case with the Quadromat Senior. We have 3 conversion passages, only 1 here with the Quadromat Senior. Additionally, here, the cylinders that are used on the conversion side, they are corrugated. So not smooth, which is not, again, not as representative. With, again, sifting between passages. In the end, we end up with 6 different flours with the LabMill and with the MLU. 14 different products in total. Something that also makes a big difference between the LabMill and its competition is the automatic product transfer. There is no automatic product transfer with the LabMill. So that means that you have manually to take every product and to place them into the corresponding hopper. This can be seen as a disadvantage, of course, because that means that you have more operative time on the LabMill, but that also means that you are able to see all the products. And so you have a much greater chance to understand what's going on, to interrogate yourself about the quality of intermediate flowers, of intermediate products. This is not the case with the Buehler MLU or with the Chronomat Senior, where the product transfer is all automatized. And you have the possibility to reduce the necessary time to grind 2 samples by testing 2 samples at the same time. Actually, the breaking side and the conversion side, they are completely separated, completely independent. So you can, once you have finished with the breaking of one wheat and you are at the sizing or conversion side, then you can start with the breaking of another wheat. Then, of course, if you take a certain time to mill 1 sample, it will take less time to mill 2, and so on. So what about the quality and the quantity of the flour we'll get? So the first indicator that we will look for is the extraction rate. The LabMill provides with high extraction rate. The usual range that is obtained with the LabMill is between 66.2 and 81.5. Here, this is a study made with the Arvalis French Institute on a certain number of wheats that showed that the average hard wheat extraction was 77 and the average soft wheat extraction was 75%, which is quite high for a laboratory mill. As a comparison, this is a study that was performed in 2020 by Limagrin, where the same wheats, 20 of them, were analyzed thanks to the CD1, thanks to the Buehler mill, and thanks to the Chopin LabMill. And what we see is that whatever the wheat, we have a greater extraction with the Buehler than with the CD1. This is expected, but extraction is maybe not the most interesting aspect of the CD1. What is very interesting is that we always have also a higher extraction rate with the LabMill than with the Buehler MLU. And still, we have an excellent correlation between the LabMill extraction and the Buehler MLU extraction. More recently, in 2024, the source is still confidential because the study hasn't been published yet. Another study has been performed on 3 different US wheats, high protein wheat, medium protein wheat, and low protein wheat, and they have been qualified thanks to Buehler mill and LabMill. And as you can see, the extraction obtained is either really close or, and in any case, always higher with the LabMill than with the Buehler mill, making it probably the most efficient mill in the world when it comes to increase the extraction rate. But still, we can increase the extraction rate without damaging the quality. If we do the same study here with the same flowers, the range of ash content is actually very low. Is in this first study between 0.42 and 0.76, with an average at 0.58, which corresponds to for French people type 55 flour, or American, that would be an all-purpose flour, a 000 type for Argentina, 550 for German flour, but basically a white wheat flour. And this has been confirmed again with the same study here, comparing the Buehler mill and the LabMill. The ash content obtained was always the same with the Buehler or with the LabMill. And to give you an idea of how representative we can be, we also have made a study a couple of years ago, grinding 150 wheats from the entire world, from South Africa, Argentina, Kazakhstan, India, France, Spain, Greece, Turkey, the US, Canada, Australia, Italy, and the UK. So those 150 wheats, we have grind them thanks to the LabMill, and we have analyzed the flour, the resisting flour, with many different methods, including Mixolab, Estematic, Protein, Farinograph, Extensograph, Mixograph, LVA, and also different baking methods. And what we can observe is that we have a very wide variability of behavior. Just to give you an idea, the W value obtained was between 42 and 500 and 500. Water absorption was between 48 and 66. Damage starch, again, very different. Protein content, very different. Stability between 1 and 45.8. And even the volumes, they vary on a great scale, meaning that whatever the type of wheat, whatever its hardness, whatever its where it comes from, you can produce a flour, and this flour will have a representative quality. And in order to better illustrate that, in the same study that is, well, still in progress, the flour produced from the Buehler mill, the LabMill, and the Quadrimat Senior were analyzed in baking tests. And in the end, specific volumes and the number of alveoli were assessed. For the specific volume, what we can see is that for the Buehler in blue and the LabMill in orange, we always have very similar results, whilst for the Quadrimat Senior, we have lower volume for the medium protein and a higher volume for the low protein wheat. And for the alveoli, well, we have very close results for all meals between high protein wheat and a medium wheat. But for the low protein wheat, we still have very comparable results between Buehler and LabMill, but very different results, actually the same as the other for the Quadrimat Senior. Meaning that in this specific application here, the Quadrimat Senior would not be discriminant, whilst the Buehler and the LabMill are discriminant. So in the end, we really have two options for two different needs. If you need to compare, you want to trade with based on certain quality. You agreed with your provider on a specific quality, you want to check that. The best thing that you can do is to rely on a tool that has fixed setting and a specific way to use that, even better if it's standardized. And that's the case of the CD1. That really makes it the best tool to compare results. Perfect for laboratories. Then if you want to understand what's going on, if you want to anticipate how the wheat will behave in your production, if you want to anticipate how how to blend your different fractions, or how to correct using what enzymes to do enzyme dosing, for instance, then you need to have a tool that is representative enough. And for that, the LabMill, for all the reasons that we explained, because it has been designed to be as representative as possible, because the settings are not fixed and you can tailor them according to a specific application, then this is really the best tool to understand. So unique for predicting. So in the end, I would say just make your choice. And of course, let us know if you have any questions. I would be happy to answer them. I hope I was not too long. And again, any question, please use the Q&A. I would be happy to answer. Thank you very much for your attention. So far there is no open questions, but again, I'm still here, so do not hesitate. Thank you, Gerald. So I see that someone has raised an hand. Please use the Q&R section. Q&A, sorry. So I have a question. What was the sample size for your LabMill survey? If you mean the survey that we did where we asked the users, so how many users, I guess, have we interrogated? I think yes. Well, we reached out to most of the people that we can think of, we did not have much because it was at the beginning of the LabMill, but I would say maybe around 10, 12 people, something like that. A little bit more, maybe. I can check. Any other questions? Well, of course, if there is no other questions, feel free to contact us at any point using the sales@kepmanalytics.com address or by contacting me directly. I think I put my address in the presentation. And of course, you will be sent the recording of the presentation with all the information to contact us. So don't hesitate at any point. So thank you, Prancy. That's it. Thank you so much for your time and the explanation. So if there is no further questions, we will close this presentation now. Again, feel free to reach out at any point. I have a question here. The sieve arrangement for the LabMill and CD1 seem the other way around compared to traditional methods. What do you mean, Gerald? Can you precise? I'm not sure the sieve arrangement. What we do with the sieve is that it's, of course, it's open small at the beginning. So we get flour first and then higher granulometry and then even higher granulometry. And in the end, we get the bran or the middlings, if you prefer. And this is because we are using rotary sieves and not Planchister's method. If this is what you mean by traditional methods. Yes, okay, thank you. So yes, this is because of that. This is not like a Planchister. You don't have like this is not different sieves on top of each other. This is a rotary sieves. In order to have a more compact instrument, we use a rotary sieve. So the product goes through, all the product goes through the entire sieve. So first you have the lowest granulometry, and then this is getting coarser and coarser. Another question is that, is CD1 capable of helping choose the wheat blend tempering? And after analysis of your mixer, choose the right enzymes? Yes, absolutely. The CD1 is still capable in helping you do that, of course, because you will get an end flour that is close enough as the industry. This is not the main aim, so it will be most representative with the LabMill, but still you can have a good approximation with the CD1. Any other questions? So if this is it, thank you so much for your attention. And I hope to see you again soon for another webinar. So stay tuned. Thank you so much.